Oh, you can't hear anything I'm saying. Good morning. Good morning, Glazer. Good morning, Tyler. Good morning to everybody else who's watching, if there is anybody else. Um, when you saw me moving my mouth, what I was saying is I understand it's gotten a little crazy there again, so hopefully whatever crazy is going on around you, it's not disrupting what it is you want to do in your lives too much. Good morning, Atsuya. So, we are in week... morning, Ursula. We're in week 6, and I know I do this countdown, but it feels good to sit here every week and say, like, we're already in week 6, which just means we're moving along pretty good. We don't have a whole lot of new content today, so I have time. If you haven't, hopefully you have had a look at the first project, but if you haven't, we're going to get a brief look at getting you started on that today, because we should have plenty of time to do that. So I'm glad you could be here if you're watching the video later, because they shut off your power or whatever is going on. Sorry for that. Hopefully it somehow settles itself out sooner than later. That's a lot to deal with. Okay, so I'm going to do what I always do. Just kind of look at where we're at in the semester and look at the content for the week. And then hopefully you have a similar experience. Hopefully at least that's true for a lot of you. That once you get down and you start sort of putting your hands on your keyboard and your eyes on some code, now you're in control of the situation, and it feels good to sit down and sort of have complete control over whatever it is that happens in the form of the software that you create. So I hopefully you get that feeling, because that's a feeling that I like to have. Okay, so we are in week 6. So we're adding one instruction, one x86 instruction, which is multiplication. It's the first one. You know what it is. It's how you multiply numbers. And we've already dealt with some of the basic problems with what actually goes on the processor. Is if you multiply two 8-bit numbers, you may get a result that doesn't fit in 8 bits anymore. But it's also the first instruction that's just a little bit weird in terms of its history at Intel. So there's some questions in your homework about this, and I'll also reference it a little bit while I'm talking at you. So the first project is due on Sunday, October 11. So that's one day less than 2 weeks from now. So now's a good time to start if you haven't started. A lot of you have probably written a vending machine or a little shop type of program before, so that's maybe familiar ground for you. It's largely about just doing some simple counters and a little bit of simple arithmetic, with the theme being that the person's buying products from a machine or a store. Okay, but we'll handle the week 6 stuff first, and then we'll do some project 1 stuff. Okay. So that's the main thing. We're going to add the x86 multiply instruction, and then we're going to practice, get a little bit of extra practice doing additions and subtractions, adding in multiplication, and then also detecting when errors happen. Because at the assembly level, at the processor level, as we talked about last week, adding or subtracting or multiplying things can lead to errors, because you may get a result that's negative when you're using unsigned numbers, which can't be, or too big for the destination register. Adding two 8-bit numbers, for example, the result is not guaranteed to fit in an 8-bit register. So we'll use E-flags and condition codes to detect when errors happen. And then I'll point out to you where you have opportunities to kind of get a feel for this by running the program you create this week and then punching in numbers purposely to cause errors to happen and observe the errors happening. Okay, that's the goals. The reason why there's a Wikipedia reading here about opcodes is because your book refers to opcodes but doesn't explain very well what an opcode is. So I thought it's a lot easier to understand um, the multiplication section of your Art of Assembly book if you know what an opcode is, because the author references opcodes but doesn't really offer a good definition of what they are. So I reference a Wikipedia article for that. I'll come back. No, actually, the homework is, as always, 10 review questions that I write out of the readings. It's the lab I'll come back to. It looks like there's a scary amount of words in here, but because I'm not actually there where I can talk to you and you can ask questions and we can sort of swap ideas, I feel like I have to give you more text to explain the purpose of the exercise. So all of this stuff in the description is really just trying to explain to you what's the point of it. And so sorry for the extra words, but sometimes I feel like a little bit of extra explanation might help some people understand why am I doing this. So we'll come back to this. It's another one of those kind of fill-in-the-blank programming exercises, which for this class is one of the better ways to get the experience that I want you to have, is just to look at how it works and then experiment with it. Piazza. So the discussion prompt looks like a lot this week, but it's really just each one of us adding a little piece of our own observations to a discussion. So as an example, you can do it after you implement this week's code. You can punch in a couple of numbers that you know should cause an error, and then share with us in the discussion, what did it look like when I punched in? What happens when I add 1 to 255? What does the result look like in HLA? So you don't have to do any massive research here. It's really just after you've implemented the lab code, punch in some numbers and observe what happens, and then sort of share your observations in the discussion. So it looks like a lot of stuff again, but really it's just some ideas about things you might experiment with, observe, and then share in the discussion. And then the reminder, so I'm going to come and touch on individual project 1 today because that's due in just under 2 weeks now. Okay, so mole is kind of weird, so what I actually should do is bring up the book and sort of explain to you why at least I believe a lot of us look at the mole instruction and think, well, that seems a little bit weird. So here's the reading. We're focusing on mole. So the mole instruction is for unsigned multiplication, and imul is for signed multiplication. We do not have signed numbers in our code yet, so we don't have to worry about imul. But this is the first time where you're encountering an instruction that's different for signed and unsigned integers. So addition and subtraction are the same whether or not the numbers are signed or unsigned, but with multiplication, and then division coming up soon, with multiplication, it's a different instruction when you're multiplying unsigned numbers versus when you're multiplying signed numbers. So you really have to pay attention to this when you're writing assembly or assembly-like code. Am I multiplying signed numbers or unsigned numbers, because they use different instructions. We are doing unsigned this week, which means mul. Okay, so our focus is mul. We will eventually use imul because eventually we will get signed integers into our mix. Okay, so if you're looking at mul, one of the things that's weird looking about it is that, let's see if I can highlight this without accidentally highlighting more stuff. If you look at the mul instruction, I'm actually going to confirm you can see what I see. You can. The standard mul instruction in Intel processors only takes a single argument. So that's weird because, well, where's if I'm doing x times y, if this is the X or the Y, where is the other one? So if this is the Y, where's the X? And the answer is it's implied. So you have to be aware of how the Intel mul instruction actually works. If I put mul BL here, Intel always assumes that the X part is AL, always. So for 8-bit multiplication, the X part is always AL. For 16-bit multiplication, the X part is always AX. And for 32-bit multiplication, the X part, X times Y, the X part is always EAX. So you sort of have to get used to the idea that the other part of the equation is implied. It's hardwired to the multiplication instruction. The other thing to note is that when you do 8-bit multiplication, you get a 16-bit result, which is quite nice, which means that you can't, in reality, overflow multiplication because your result is always stored in twice as much space. So that's nice to know. Now here's something that's a little awkward. The way Intel does 16 to 32 bits is not to use EAX, but is to actually bundle DX and AX together. Now you don't really have to worry about this yet. You are going to have to worry about this weird bundling when we get to division. But the way Intel has implemented it is it treats that combo, DX and AX, as a 32-bit destination register. So DX is 16 bits, AX is 16 bits, together they make 32. That's how it actually works on an Intel processor. DX has the higher 16 bits of the result, and AX has the lower 16 bits. You don't really need to know this for programming right now, but it's a matter of making sense of what does this mean. What it means in programming is that it's a pain in the rear to do 16-bit multiplication, because you then have to figure out how do I get those two separate halves of the result put back together. The same thing applies to 32-bit multiplication. How do I get those 64 bits of results somehow put back together? For the most part in our class, we're not going to worry about it. For your own experience, it's just to have seen that this is how it's done on this particular processor. There is another question, by the way, because when you're reading the book, you see like Reg 8 here, Reg 16, Reg 32. So in your book, that means an 8-bit register, a 16-bit register, a 32-bit register. Any general purpose register that fits the right size is what that documentation means. So when you see a mem8, that means an 8-bit variable. A mem16 is a 16-bit variable, and a mem32 is a 32-bit variable. So what it's telling you here is that when you use the official Intel mul instruction, you can use it on 8, 16, or 32-bit registers, or 8, 16, or 32-bit variables that you have declared in memory. Those are the actual sort of Intel instructions. Now let me cover the opcode bit so we can get to the more practical stuff, like, okay, what do I actually need to know to do the lab? This is just informational, and then we'll look in a second at, okay, what do I actually need to know for the lab? Okay, there's a reference in here, right here. So, unfortunately, it says, when Intel went to implement a multiply instruction, they didn't have enough bits in their opcode to add these new instructions. So what does that mean, their opcode? So I gave you a Wikipedia reading about that, but the opcode is basically the instruction that you write has to be translated into machine language, binary. So for every instruction, like add, sub, mul, move, the instruction itself and the operands have to be translated into binary. And we call that binary code opcodes. So an instruction like mul that we can mostly read as humans is translated into a binary opcode. So what this is telling you is that Intel actually ran out of numbers to represent the multiplication instruction with 2 operands. I don't know if that makes a whole lot of sense, but I pulled up a picture here just to show you an example. So this is an example of a binary version of some instruction. Let's pretend like it's mul. And then some extra bit of information, and then a binary encoding of whatever the operand is. So each one of our instructions has to be encoded like this for it to be actually executed by the processor. Again, this is mostly informational, but when you write an instruction like a mul instruction, and then we run the compiler on it, the compiler actually translates this into the binary opcodes. So anyway, what the Intel engineers discovered is, oh, we've already used up all of our opcodes. So how do we fit more instructions into less opcodes? And the answer was, well, we're going to have to use part of the operand encoding section to fit new opcodes. So they had to chuck out one of the extra operands that would have been encoded to fit the instruction itself. So in other words, they found that they ran out of, this is an example, right? But they ran out of 3-bit codes, so they ended up having to spill over and, let's say, use 5 bits, which meant that they ran out of space to do all the operands that they wanted. So let's pretend, for example, that this is a 3-bit opcode and then 2 3-bit operands, let's say. So if Intel said, well, crap, we've already used all the 3-bit combinations that are available to us, so we're going to have to take some of these bits. So let's say now we have to have a 6-bit opcode for multiplication. Well, that meant there were only 3 bits left after that for operand, so they had to design around that problem. Okay, well, how do we do that then? Well, let's just make AL be the other operand. That way it can still be programmed. All right, so that's probably a bad way of describing it. I hope that made some kind of sense for some people. Doesn't really matter at the end of the day. You can go back to a high-level language and say, thank goodness that the high-level languages just make all these problems disappear for us. But that's why I asked you to read the opcode section, is so that you have some sense of what they're talking about. It's the actual binary encoding of the instructions that we write. Okay, so if we scroll down in the reading, you're going to get to this section down here, where the author of the HLA language and the text says, to help reduce some of the problems using these instructions, HLA has actually provided us with an extended syntax that makes more sense for humans. So the author of HLA and the author of our book has actually sort of added some helper instructions so that we can write arithmetic that feels a little bit more natural. And these are the ones we're going to use. So instead of, going to scroll up again, the true x86 instructions, where you have to constantly remember that, oh, AX, this implies AX, or oh, this implies DXAX, and so on. What the author has done is they have instead made some more explicit instructions so that when we're writing code, it's more obvious and easier for us to remember what is actually happening. So we're going to use this form, but there's a catch to it. Do you notice it says reg8 AL? So what that means is, even though it's an extended syntax, this second part has to be AL. You cannot change it. It has to be AL or you will get an error. So any general purpose 8-bit register for the first one, but specifically AL for the second one. So he hasn't really changed how it works on the processor. He's just made it slightly easier for us to program. Now you might see something else going on here, which is he's got an 8-bit source and an 8-bit destination, when in reality the destination for 8-bit multiplication is 16 bits. So one of the trades we're going to make here is to write a simpler instruction. When we do 8-bit multiplication, we're going to get an 8-bit result. That also means that we're going to have to do a little bit of extra work to detect overflows, detect situations where multiplying two 8-bit values results in something that's bigger than 8 bits. So notice his 16-bit helper here goes to 16 bits. Officially, that should be the little DXAX combo, but this is the way we're going to write it because it's just a lot simpler to understand, and the point is to just gain a little bit of insight into how the processor actually works and not to master x86 assembly language programming per se. So where the HLA language makes it easier, sometimes we're going to take advantage of that. So these are the ones we're going to use. Because we're using the HLA form of these, we get some help. You'll notice in the Intel ones, the only things that you can do are registers and variables in memory. But if we use the HLA ones, we can use registers, memory, or constants, which is super helpful if we want to just multiply something by 2, let's say. We now can use 8, 16, or 32-bit constant values. Okay, so that's a lot. It's a lot to take in. You're going to do your practice for this week's lab is just writing one of these and just stopping on it to consider what you're looking at. It's not hard, but mul is weird, which is why we're only doing this instruction this week, is because it's the first kind of weird one that we're doing. So we're going to use the HLA style, at least I am, which gives us all these options. The trick here is that you have to, when you're using the HLA form, you have to use the prescribed destination, AL, AX, EAX. You have to use those. So the second part cannot be anything other than AL or AX or EAX. It has to be that. Pardon. Okay. So that's the mul instruction. So the questions in the homework are just asking you to read, and maybe now what I said will help you a little bit in hunting down the answers, to make a little bit of sense of what this mul instruction actually does and why it is that way. So the reason why the mul instruction is so weird is an accident of Intel's history, because when they went to implement it, they discovered that they had run out of enough opcodes to represent this new instruction. So they had to steal some of the operand bits to encode the operation, which means that they had to give up one of the operands. Okay, that's that. This picture I got was just so I could show you that this is kind of what an opcode looks like. If you were to look at the binary of a program, that's what they would look like. Okay, so lab. Okay, so I'm going to do a fair amount of the walkthrough here, and apologies if I'm sort of constantly stealing your programming thunder. I think this week, though, since you have the project coming up, that you have plenty left over to express yourself in. But the point is to create a small program that you can then sort of explore by punching in numbers just to see what happens with your arrangement. So I'm going to go start up the whole process of getting a lab. So I'm going to click on this link. This one's only got 5 elements in it, 5 numbered items to work on. So go to the raw. And then let's see if I'm well, I can go ahead and copy this. So I'm going to go ahead and Control A, Control C to copy all that code and then go over to my virtual machine, which I'm going to now pop up. While I'm setting up, my other hope, by the way, is that you're getting a little bit of chance to just sort of review the basics of programming while we do this. So I've gotten this feedback from people in the past, so I don't know if everybody feels this way, but because we're using HLA, it gives you a chance to practice writing functions and loops and if statements, and kind of it's a good chance while you're exploring the assembly side of things to also strengthen your basic programmer skills. So I've opened up the assembly folder. I'll open up the terminal. I'll open up the text editor. This one usually takes a second. Paste my stuff in, Control V. I may need to stretch this window out a little bit. Okay, and then make sure I save it as desktop assembly folder 6.hla. Okay, so hopefully by now the programs are getting a little bit longer here and there. So hopefully you're starting to get used to what they look like. I know that it looks like a mess. So again, it's another thing to appreciate about high-level programming languages is that they make the programming job look a little bit less messy. Some of them make it look a lot less messy. Okay, so let's go down here and I'll just make sure that you are armed with enough information to get started on it or to finish it. And then I'll switch gears and look at project one a little bit. The get number function has already been implemented, so that's good. The play again function, you've seen this one a whole bunch of times now. It still has a piece in here just to kind of give you some points for repeating a thing that you've done before. Hold on, I messed up my little setup here. Okay, that's what I want. So there's the first element, which I won't do, but that one you've done before. All right, here's the second element. Now I'm going to do add and then sort of show you the kinds of experiments that you might consider running so that you get a feel for it. So remember that when you're doing arithmetic, you often need what is called what you'll see called in people's in textbooks and stuff a middleman register. So you need some register to receive the results of computations. So item number 2 is simply moving the first of the numbers that the user inputs into a register. The reason we're doing that, you may remember by now, the reason we're doing that is because if we're going to do arithmetic with this first number, we need it in a register as a middleman to do the arithmetic. We can't do add two variables, two mems together. One of them has to be a register. So the value of number 1 goes into BL, and then we can add the value of number 2 to BL. So now BL contains the sum of number 1 and number 2. The nice thing about middleman registers, by the way, is that it leaves your original variables unscathed. So number 1 still has its original value that was input, which is useful. Number 2 still has the original value that was input, and BL contains the result of summing the two together. Okay, then we do something that we looked at last week, but now I'm going to have you do more of that, which is to check and see if there was a carry. So in this situation, and sometimes overflow will work, but in this situation, the way we're going to see if the result of adding number 1 and number 2 together doesn't fit anymore is by checking for a carry bit. And the way we do that is with an if statement and then this @C carry bit. And what we're doing with that is we're checking, how to explain this. When we do this add, it's going to actually do the addition on the values, and if there is a carried over piece of value, it's actually going to flick on a bit in the E flags register. And so what we're doing with its at C is we're actually going in immediately after this add to see if the add instruction flicked on that carry bit. So if the add instruction does flick on the carry bit, that means that the computed result was too big for an 8-bit register. So that's how the circuit kind of works. It does the add, and then if there is too much, it will flick on the carry bit, and we immediately check that. Now, let me see if I can show you a picture of that. I can show you a picture of that. So let me switch views real quick. So if we were to sort of look at a blow up of the E flags register, it's really just a whole bunch of little flags, the switches that can be turned on and off. So when you run an add instruction, if the result is too big, the add instruction will actually come in here and automatically, here's the carry flag right here, it will automatically flick on this bit. And the reason why it does that is because then me as a programmer, I can immediately check to see if that bit has been flicked on. I know that the add instruction had an error in it, and I can do something about it. So that's kind of what E-flags looks like if it were blown up gigantic. It's got all these little switches. Some of them are unused, but the carry flag is very interesting to us. The overflow flag, which is sort of up in the middle here, that one's interesting to us. So we can check after an arithmetic instruction and see if any of these switches was turned on. That is an indicator that something happened. All right, I don't know if that made sense. I hope that it makes some kind of sense. So back to the code. So what we're doing here, do an add, understanding that that switch might turn on, so we check for it. Did the switch come on? If it did, oh, the result was too big. So we're just going to short circuit that part of the program because, well, the result's too big. If the result wasn't too big, then we're going to do a little math quiz. Right? Okay, so this is valid. So we're going to ask them to tell us what they think the result is. And then we're going to check to see if what they think it was is what it was. So one of the reasons why we use BL up here is because down here we still want BL to contain the original correct sum, and AL will be their input that they type in. So we check their input, AL, against the computed sum, and if they match, then they get a cookie. Otherwise, we tell them what the correct result was by typecasting BL. Now that's a lot. We're going to run it right now just to see how it works after we added those two instructions. Except for I haven't implemented play again, so I will comment that out of mine. Comment this out of mine and just run it once at a time. It's fine. So let's do some experiments real quick just so you can kind of get what I'm going for here. So we just did the add section and that's it. And so the program is going to have a for loop. So I'm going to have to use Control-C to kill it. That's fine. Sorry, I lost control of the scroll. Now the program is going to prompt for and read in a number, prompt for and read in another number. Because I can type these numbers in, I can sort of fiddle around with what happens if I put 255 and 1. That should be too big, and I should see an error happen. We'll find out. Okay, good question. I'll go hit that. So the question is, what's this console.cls? So this is an HLA library function, and it clears the screen. So what this does is at the end of every pass through the little math quiz, it'll clear the screen before it makes another pass through it. Super handy. Most languages don't offer a built-in screen clearing function like this. So it's something I like about HLA. That should actually be right there. Good question. So he's asking about line 100. They're asking about line 100. Console.cls. So yeah, it'll clear the console screen so when the program loops back to get another pair of numbers, that happens on a blank screen. So I put one up here as well, so that at the very beginning of the program, whatever was going on the screen gets wiped off. I'll show you actually when that happens here. So let's go compile that. Hopefully it just does compile because I have unimplemented stuff, thank goodness. So when I run this program, it's initially going to clear the screen. So all this stuff that's currently here is going to get cleared off by the console.cls. So there, the screen is clear, is that initial console.cls. Now I'm going to put two correct answers first, so I'm just going to put 1 and 2. So it's already computed using BL, the sum of those two numbers, and because there was no overflow, I now get the quiz part. So the program's actually sort of asking me what's 1 plus 2, and if I type 3, it should say, well, it cleared the screen, but if I scroll back up, that is correct. That's because it cleared the screen because of the one at the bottom, which I probably should have commented out, but that's fine. We'll just scroll. All right, so now it's looped around and it cleared the screen. So numlock is off. So now I'm going to do something naughty because I know that if I add 255 to 1, that's 256, and that doesn't fit anymore. So what does the program do? Because it cleared the screen, I got to scroll back up. But it detected the result of the error. So it detected with that @C check, this thing right here. My code detected that there was something wrong with the addition. So instead of giving me the quiz, it just said, sorry, those two numbers don't compute. I'll do another. I'll just say, like, what if I try 255 and 255? That's ridiculously too big. So in theory, that should still say, cannot compute results. So that's the idea. And so kind of once you get it implemented, your challenge is to see what kinds of values you can punch in and what happens in the program. If, by the way, you're working along with me, you're stuck now because there's no way for the loop to break, so just use Control and C, Control C, which you can kind of see on my screen there to kill the program off. So that's the challenge here. There's a sub one. So all it says for the subsection is now repeat the whole thing except for doing sub. You will still check the @carry bit. So it's going to be very, very similar to add. So I'm not going to do that one. I'll leave that one sort of for your main new challenge. What time is it? Okay, we're still okay on time. I will do a little bit of mul. So you can see what that looks like. So for mul, repeating the entire thing for mul. So basically, I'm going to move number 1 to BL. And then, let's see, how do I want to do this? No, I can't. I have to move number 1 to, well, I'll show you the problem. So what I want to do is mul number 2. So I'll do it wrong just so you can see it. That's kind of what I want, right? The problem is, I'm not allowed to do mul with BL. This has to be AL. It has to be. HLA imposes that rule on us in part because that's what the Intel processor is doing underneath, is actually forcing you to use AL. So because I am required to use AL here, I need to load up AL with the first number. Now this causes a complication later on in this sequence, but we'll deal with it. So just to point out to you, that mul has to go to AL. Add and sub don't care, but mul does. It has to be AL, which means that the middleman has to be AL. So in this case, we're told by the note that we're checking overflow this time. So for mul, it's not the carry bit, it is the overflow bit. put a note there for myself. Now, me personally, I'm just going to take the same output. Just because that would please my sense of order to have it look the same everywhere. Mole error this time. Checking overflow after multiplication, because that is the flag that's set for mole. For add and sub, it's carry in our situation. For mole, it's overflow. Okay, so now you got to be careful, because if you copy the same routine, I'm going to strip out some of the commenting so you can see what's going on. So if you copy the same routine, I'm going to take some of these out. You have to think a little bit here about what's about to happen. Times equals. Okay, so now you got to be careful. Because they're about to put a number in and they're going to overwrite AL with their input. So you really got to pay attention here, because when you get here, your nicely computed result is about to get blasted by this input. So you can't let that happen. So what you need to do is make sure that you copy that computed result somewhere else so that the input doesn't ruin it. So I'm offloading or copying this computed result that I mulled into BL. And the reason I'm doing that is because this get number is about to overwrite AL with their input. So you got to pay attention for that kind of stuff. So if I allowed this get number to happen without doing anything about my nicely computed result, then I'd lose my computed result and I'd have to do it all over again. Remember, the reason why it had to be AL is because it has to be AL. You cannot mull into anywhere else but the A register. So it had to be that. Okay, so I copy the answer off to the side. Then I get their input, which is going to go in AL. And now, though, basically I can use the same logic again, right? Now AL is their input. BL is the computed value that copied over. And then I can use the same logic. So that's why end of mull. Hey, that's going to bother me. I got to fix that. I'll fix that, but that's just a comment. All right, that's actually complete. So if you're, that one's a little bit harder because of the extra restrictions that you have to work around and consider. Mull has to go where? It has to go into AL. You cannot change that. And because that's true, if you do something later that might affect AL, then you got to be careful about your computed result. If you don't set aside or offload your computed result, then you're going to lose it, and then you're going to have to recompute it. So just copy it off to the side, and then everyone should be happy. Let's try it. So I'm just going to do little stuff like 2 and 3. That's 5. I forgot to update the prompt, didn't I? Yeah. 2 times 3. 2 times 3, I know this one should be 6. I have to scroll up because I haven't fixed the play again part, so that is correct. I'm going to rebuild it just to... Alright, so now let's do something that we know would be too big. So, like anything over 255 is too big. We could do 25, what's 275? How many 25s is that? 4. Is that 11 of them? I think 11 of them. So 25 plus 11 works just fine, but 25 times 11 is too big. So let's see if that's true. I'm going to get it wrong. I got it wrong on purpose. But anyway, notice that the mole then didn't work because 25 times 11 is 275, and that's way too big. So in this case, the quiz couldn't do the mole part, but it could do the add part. So the whole design of this thing is not to be like an awesome math tutor. The whole design of this thing is to hopefully give you an opportunity to develop your own feel for the limitations of arithmetic on Intel processors. That's the idea. And the limitations of arithmetic on different sizes of numbers. So we're using 8-bit numbers here because the range is smaller and easier to work out in your head sometimes. But it's the same problem if you go to 16-bit or 32-bit values. They have limits. This is true, by the way, in high-level programming. In many languages, like C++, it's very easy to overflow math in C++ because it doesn't have a built-in capability of prohibiting that. So you have to be a clever programmer sometimes to detect it and deal with it. Some languages, though, do have sort of a built-in ability, by the way, to just accommodate you. Okay, that's the lab stuff. I hope that's enough. That's the complete mole section. And now I fixed the prompt so it has an asterisk and not a plus in it. I did nothing on the subsection, so that's completely undone, but hopefully now you know you need a middleman. You need to pay attention to which registers are being used for what. And you're going to know when you run the program because you're either going to match up results or get the errors you predict or not. I also didn't do the play again function, and I commented out a couple things because I knew that play again doesn't work anyway. Alright, so I took away most of your fun on the lab. Sorry about that. Because I want to get to a little bit on the first project. So if you need a couple of seconds to breathe, this is a good time to take it because I'm going to switch views, take a sip of tea, and look at the lab right up. That's what I want. Okay, so the project. So I went back to the home page and I clicked on the project. It's got a lot of description on it, and again, I try to fill in gaps that I anticipate might happen because we're fully online. So there's probably more words here than I might normally use to hopefully explain to you what this program is supposed to do. And I'm going to talk a little bit about it here this morning to get you started on it. It's a vending machine, so the idea is that a person buys a product and then they pay for it, and you have to make sure they pay enough, and then you give them, do I even require a receipt here? Yeah, with a receipt. So this vending machine keeps track of your entire shopping session, as it were, so that when you walk away from the machine, it says, hey, here's all the stuff you bought. You could also think of it as a shopping, like a grocery store or something. So you go in and you buy some items. You pay for them and then you get a receipt. That's the idea. Why we're doing this vending machine is because it allows us to use all of the skills that we've acquired, mostly up to this point, except for the change-making part, which we need something from next week. But basically what you need to do this project is you need to be able to write if statements, loops, create variables, and then do math, add, subtract, multiply, and divide to solve this individual project. So after next week we'll have divide, and then you'll have the last piece that you need to actually fully complete the lab. So that's why it exists, is because it's a place that hopefully most people understand the basic problem, and it lets you practice what we've learned so far about x86 assembly. So there's a lot of words, but I also added some pictures. The actual what you're scored against is down here in the requirements section. So when I go to grade these, I'll be looking in your program, in your code, and your implementation for these features. And then I also thought it might be helpful for some of you if you could see screen captures of how mine works. So you have 5 products and the ability to exit. So I don't remember if mine works. Yeah. So the way mine works is every product has a price. Every product has its own counter of how many in stock I have. So every time you buy a water, the water in stock goes down. Every time you buy a soda, the soda in stock goes down. That's using the sub instruction. And once an item, so in this picture, for example, I hope you're seeing the same picture. You are. So every time a product sells out and they select it, they can no longer select it. It just says, sorry, we're sold out. And then once they've decided to exit their shopping section, there's shopping session. Now is the checkout routine, is how I did it. So you could have them pay for every individual item they buy, but it's a lot easier if you just keep a running total of how much they owe you, or compute how much they owe you, and then make them pay. So you got to make sure they pay enough. So if they put in too little, I kept track of how much they've currently paid and how much total they owe. So you notice on the next screen, after they pay 200, what they owe is still 100 against the original total of 300. That's 2 variables. Now they pay 141 pennies or credits. So that's enough. That covers the 100 that they owed me, and then they get a receipt. So they bought 2 waters, 1 soda, 4 candies. Each of those has its own separate computed total. Then the grand total, and then the change. So the way I want this to work, because we don't have floating point numbers, all we have is unsigned integers. Pretend like this is all in pennies, or coins at least. So when they say I'm going to pay 141, it's like I'm paying 141 cents. So at the end, if you still owe them 41 cents, what they get back for that is 1 quarter, 1 dime, 1 nickel, and 1 penny. That's the 41 cents that they get back. The reason why the change component is there is because that will require that you use division. And I want that there so that you get to use that instruction. So this last part, computing change, we will get the div instruction next week, and then you'll be able to do that part. Okay, so that's how it works. I'm going to get started on it just to draw your attention to some of the things that you're going to need, and in theory maybe want as well. I've got maybe 5 or 10 minutes, so let me make a new one. I don't want a new window, I just want me a new file. How do you do that? Create a new document. Ah, there we go. I had never clicked that. It seems obvious. Okay, so I'm going to fire up my vending machine. You need documentation, but I'm not putting it here because it takes up space on the screen, and it's distracting, I think, for you if you have to look at my documentation. So I'm just reminding you, you are required to have it. It's 25 points. Worth of the project is simply that you put documentation at the top. The name of it, your name, and the date that you completed it. So I will call this project 1 HLA. Hopefully I don't overwrite something with that. Okay. Some of you are doing, oops, sorry, thank you. Oh yeah, you don't see anything. I did. I guess I could troll you guys if I wanted to and just be tapping away. But thank you for catching that, because that would stink if I did all that and then you couldn't see a thing of what I did. So thank you. Okay, so there's what I've done. So when I was saying the documentation part, I'm not putting it because I don't want to fill my screen. I want you to focus on the code part. So here's my setup. Just like any other, just like the labs, it's no different in that respect, of course. So things to consider. So one thing you could do is you could just sort of look at my screen outputs and then make code to do something similar. Now I'm going to use procedures a little bit just to suggest to you that you consider doing it, but you do not, I don't think you have to use procedures, but let me double check and make sure that that's true. Payment handling, yeah. It is not a requirement that you do procedures. I'm going to put one in here just to show you that you can use them, and in some places you may decide that it's helpful. But you can do the whole dang project inside of the main block, all of it. That would be fine. So let's get at kind of mirroring the display. So let's see, what is it? I'm switching over. I'm not going to switch the view for you, but I'm just looking at my screenshots. So it's a number, and then the product name, and then how much credits, and then how many in stock. Okay. So let's just, I would just start with this. Water. I'm going to show you a trick that I like. So if you want to do a tab output, which can help kind of make things line up pretty, in HLA you do standard IO.tab, I believe. Or is it standard out.tab? We're going to find out. Anyway, I'll fix this, but there is a tab character you can put, but it's weird looking in HLA. So water, 75 credits. I think it said 10 in stock. What does that look like? I put parentheses around it. Okay. So this is just one idea for how you might build up to the point where you get all the stuff going. But the first thing is maybe just work on the display, right? Just see if you can get the display working and then get it working with variables. So I'm going to go build this and see what happens. Display project 1. Okay, so it is standard IO.tab, and you can see kind of how it pushed things over. But that should sort of allow me to create nice sort of columnar output, nice columns. And I might as well do the second one, which was soda at 90 credits, 1 in stock. So I'm going to do 2 lines of it just to sort of confirm for myself. Your products, by the way, can be whatever you want. I just don't want to think about that part. But you do not have to use the same products. You don't have to use the same amount of credits for your products. You don't have to use the same amount in stock or anything. Your stuff can be all different. But slightly lower numbers is easier if you sort of think about arithmetic on x86 and the potential for overflows. Be mindful of that. And I'll show you the trick that I'm going to use to control that situation. So what I'm doing here is I'm just checking to see if the tabs do in fact cause things to line up like I think they do. Soda didn't do it, which I'm disappointed in Soda about, but I can hack that maybe. I have a feeling that that extra character right there is probably a problem. So I'm going to have to consider that. Okay, so that little extra character could be an issue. Let's see what happens if I put an extra character on water. Does it break it? It doesn't. I'm going to show you why that matters in just a second. So it looks like the extra character doesn't necessarily matter. Okay, so that's for me. Step one is just like get the basic part of my display working. Step two for me is to begin to parameterize it. What I mean by that is replace the hard-coded stuff where I can with variables. So I'm going to need some. I'm going to make variables for, not for the names so much, that doesn't matter, but for doing math it's going to be a lot easier if I have some of these things in variables. And I highly recommend that you keep these numbers small and that you make your variables big in size to minimize the chance that overflow can happen. So if you have a bunch of sort of little tiny numbers here and your variables are much bigger, then the chances of overflow are minimized. So anyway, but what we need here is we need water price. So I'm making this uns 32, even though it's a tiny value. And the reason is because I want to do math as unsigned 32 bits, and the reason I want to do that is because that is having way more bits when I do my calculations means the chances of overflow are minimized. So it looks weird. Why do I need 32 bits for 75? Technically I don't, but it makes preventing overflow a lot easier if I do 10 75 centers, right? If they buy all 10 of my waters, that's 750 credits, and all of a sudden not even the price of water fits in to 8 bits. That would fit into 16 bits, but I'm sort of guaranteed I have a pretty good chance of avoiding overflow if I give myself big variables for doing my math with. The water in stock doesn't have to be big, so I don't intend to ever do anything with the stock value other than use it as a counter. And I don't imagine I'm ever going to stock more than 255 of anything. So the prices I'm going to have to do multiplications with. That's why those are big. The water in stock is just a counter. I'm just going to count it down by 1. So that doesn't need to be big. I'll go ahead and do, I also need to know, by the way, water bought. The water bought does need to be big because I'm going to have to multiply that with the price of water, and that's going to tell me that total is going to be how much they owe for water, and those values technically could get large. So I hope that makes sense. Sometimes you sort of upsize your variables knowing that you're going to be doing things like multiplications with them, and you want to make sure you have a lot of room to grow. The water in stock part itself, though, is literally just counting down to 0, and that's it. I'm not going to multiply it with anything, but I am going to multiply prices and the amount of things that were bought. I need that for soda as well. I'm spacing them out just for your readability. My soda price is 90. Just this little counter I'm setting to 1. The reason why I set one of these at 1 is because I can quickly sell it out for testing purposes. I buy one, now it's sold out, and I'll know that quickly. And then I'm upsizing the soda bought as well. So the prices and the number that they bought I've upsized so that I can do multiplication with them and minimize the risk of getting overflow. Okay, so there's the water and soda. Now what I want here is a procedure. I'll call it a print item. So I'm going to make a procedure to print an item for the menu. And then the trick here is to look at how you're printing them and figure out what's going to change from one item to the next. Each of them has a different item number, so in theory that can be an UNZ, I think, should be fine. Each of them has a name, which is a string. Each of them has a credits. I think that's fine. In fact, I'm going to just call it item. Number of credits, which I have to look at this because the way I'm doing pricing is with UNS 32s. So I'm going to need to make sure that parameter is going to match in the future. And then the number in stock, which are going to be 8-bit numbers. So those kinds of things are hard, and you can make that easier on yourself if you want to. But I at least wanted to walk you through an example of thinking about the data types that I'm choosing and why, and when I'm setting up a procedure to be aware of the data types that I expect to be coming in. And then I'm just going to take one of these and then I'm going to parameterize it. I guess I should have. I don't want that. I don't like that. So let's see. The first thing is the number, followed by a dot, followed by a space, followed by the item name, followed by a space. And the reason why that extra space is there is I discovered that the tabbing didn't work pretty with soda. And then I noticed that putting extra space after water, it still made it work okay. So I kept the space. The number of credits here. Followed by space credits. And then right in here goes the stock, and that's my display. So now I can say, and you may decide this is totally not worth the trouble. Item number 1, which is water, which uses the water price, and which uses the water in stock. So that replaces that one. And then item number 2, which is soda. I didn't leave the spaces here because the procedure's doing that part for me. Soda price, soda, and stock. And then we'll make sure that works, and then I'll leave you one hint, and then I'll shut down because I know I'm sort of over a bit. Hopefully what you see there makes sense. If you don't use procedures, it's perfectly fine. I just know from my experience that this sort of reusable chunk of code can come in handy. If I discover there's something I want to change about my display, I only have to change it once, and it automatically applies to all of my items. So that's the main advantage here, is that now I can go back and sort of tweak my display if I decide I want it to be different. So same output. I'm just checking to see that it still works and it still lines up, so that's all perfectly good. The point here was to get you thinking a little bit about your variables and where upsizing makes sense. So if you think that something is going to be involved in a multiplication on this project, I strongly recommend that you upsize those variables because you're going to be multiplying like all the products that they bought and the price for each product, and that number could get easily bigger than 8 bits and possibly bigger than 16 bits. So give yourself plenty of growing room by upsizing all the variables, at least I recommend you do, that may be involved in a multiplication. So the prices of items are certainly going to be multiplied by the number of them that were bought. When I get to computing my totals and my receipt. And because they're going to be multiplied together, they need to match. So I've upsized both of them so that when they multiply together, they're the same size. And setting the price down at 75 means that I have plenty of room to grow into the 32-bit destinations when I start doing multiplying. Okay, the exit item, by the way, doesn't really fit with my print product, so it gets its own little output, I would think. Of course, this whole thing is going to be in a forever loop, probably. Although, for development purposes, I'm not ready yet for looping. And then I'm going to leave you one last thought, and then I got to shut down. I know, I'm sorry. So we're going to have something where we get the choice, right? And we're going to say, like, if AL equals 1, then so you're going to have a decision tree down here where they say, okay, I want to buy water. So you're going to have to do if. You don't have to do it in this order, of course, but you need to check. You need to make sure that it's in stock before you let them have it. And then you're going to do a sub. I don't know if it'll let you do this. Let's try. Can you sub 1 from water in stock? I don't know, but this is an example of what has to happen here. You're also going to have to add 1 to water bought, and so on. So I think that's probably a fair amount. I'm going to see if it compiles. If it doesn't, water permit, perhaps you meant, I did mean. What a smart compiler. It's like the rare occasion that we're seeing here where the compiler is actually useful. What a shock. I'm shocked. Okay, so we'll let you do that. So anyway, tips for project 1. You can use procedures, you don't have to, but I wanted to just kind of show you my process for doing that part. So you're going to need 5 products, which means you're going to have a bunch of variables. You're also going to need some variables probably for handling the checkout and computing how much they owe you and how much they've paid. You're going to need some variables for that. So after this week, we have add, subtract, and multiply. So all of those parts of the project, I recommend that you at least try to get to the stage where you're where multiplying the totals at the end makes sense. That way, when we get to divide next week, you can apply that to computing change. I'll probably help you with that part and come back to my little project file here. Okay, I'm done. Thanks for sitting there through all of that. I know it's probably tries your patience to listen to me talk at you for an hour and 15 minutes, so thank you for your patience. If you're watching a video later, then sorry, it's an hour and 15 minutes to work through. So have a great rest of your week. Just drop a line through your Canvas inbox or leave a comment in Piazza if you have a programming question. It's great if you put it in Piazza because then when one of us answers it, everybody else can see the answer. And in my experience, almost always, if one person has a question, a bunch of other people have it as well. So you can make a contribution that way if you have a question and drop it in Piazza. And let us work out the solution together as a discussion. That's it. Hope you have a good week. I'll see you next Monday. If I don't hear from you in the meantime, take care.